SPH4U fields 4.2 electric charges. So there are a few laws of electric charges, and they are that opposite charges attract, like charges repel, and electric forces between particles determine their strength, and charged particles can attract neutral particles. So charge is due to the total amount of excess or missing electrons in a substance, and the unit of charge is coulombs. So this is actually given by an equation. Q is equal to Ne, where N is equal to number of missing or excess electrons, and E is a constant. It is 1.602 times 10 to the power of negative 19 coulombs. So here's just a few more points on electric charges. So electric charges exert forces on each other even when they're not in contact. And every charged object creates an electric field of force in the space around it. And any other charged object in that space will experience a force from the presence of that other charged object. So to represent these electrical fields, we use field lines. And for a negatively charged particle or an electron, the field lines go inwards towards it. While for a positively charged particle, like a proton, the field lines go away from it. So if you have a negative particle and a positive particle, the field lines would go from the positive towards the negative, like this. And the field lines are going to be present regardless of whether or not test charge is present or not. So now we're going to be discussing Coulomb's law. So Coulomb's law states that the electrical force between two charged objects is directly proportional to the product of the quantity of charge on the objects and inversely proportional to the square of the separation between the two objects. So in equation form, this is given by the equation Fe is equal to K Q1 Q2 over R squared. So K is a constant, and that's equal to 9.0 times 10 to the power of 9 newtons times meters squared over coulomb squared. Q1 and Q2, those are the charges of the particles or the objects, and R squared, that's the squared of the distance between the centers of both objects. So what is the magnitude of the electrical force between two identical particles of charge 1 times 10 to the negative 12 coulombs when they're 1 meter apart? So we know the equation is Fe is equal to K Q1 Q2 over R squared. So now just plug this into the equation. 9 times 10 to the power of 9 times 1.0 times 10 to the negative 12. We can just square it because we know that they are the same charges, and all this over 1 squared. So once we do all those calculations, we get 9.0 times 10 to the negative 15 newtons. So that is the electric force. Alright, so here's another example of a question that uses both Coulomb's law and the theoretical facts of charges that we learned before. So in this diagram, find the net force acting on particle C, assuming that particles A and B's position are fixed. So A has a charge of 4 times 10 to the 6 coulombs, so this is positively charged. B has a charge of negative 2.5 times 10 to the negative 7 coulombs, so this is negatively charged. C has a charge of 6.4 times 10 to the negative 4 coulombs, so this is positively charged. So with this, we need to find the force acting on C, all the forces acting on C. So first we can start by finding the force acting on C by A. So the call that like charges repel. So both of them are positively charged, so this will be repelling it. So the direction of this force will be in this direction, which we've already been given in this question. So we will have Fe1 equals to K Q1 Q2 over R squared. We can call this AC. So that's equal to 9 times 10 to the power of 9 times 4 times 10 to the negative 6 times 6.4 times 10 to the negative 6. And all of this would be equal to 0.3 squared, and that's because there's 30 centimeters between A and C. So this comes out to be 2.6 newtons, and it's going towards the light. Now we had to find the force acting on C by B. So same equation, so let's just sub in the numbers. So we get 9 times 10 to the power of 9, negative 2.5 times 10 to the power of negative 7, and 6.4 times 10 to the negative 6. Alright, so that's all over 0.1 squared because there's only 10 centimeters between those two. So this comes out to be negative 1.44 newtons, but no matter, this is the light because of the reference frame, so that's actually 1.44 newtons to the left. So now we need to find the net force acting on it, so I'm just going to do that math up here. So net force is equal to F1 plus F2, so that's equal to 2.6 minus 1.44, so that is equal to, so this comes out to be 1.16 newtons to the light, newtons to the light. So sig figs, there's 2 sig figs, so therefore the average force acting on C is 1.2 newtons towards the light.